7 fundamental properties of matter. One of the most common examples of electric charges is static electricity, otherwise known as temporary electrical properties. And one of the prime examples of this is this balloon that's attached to my head at this exact moment. One of my hair and the balloon have opposing charges, which allows them to attract. One has a negative electric charge, a negative charge, while another has a positive charge. And as you can see here, they both have the same amount of charge, 1.6 times 10 to the negative 19 coulomb. With effects like this, there really isn't one side that has more than the other. It's always going to be an even exchange. If only 3 electrons were exchanged, then it's only going to have a positive charge of 3, while a negative charge of 3. It's always an equivalent exchange. And one of the most prime examples of static electricity that we all know, and depending on who you are, love or hate, is thunder and lightning. And what occurs with lightning can be more easily explained with...
So in 1785, Charles Augustin de Coulomb proposed his theory of Coulomb's law, which is your electrostatic force is going to equal K, which is our constant of 8.99 times 10 to the 9th, multiplied by 2 charges divided by the distance between them. So Coulomb's law is the theory that talks about how 2 charges affect one another. So we have 2 charges here. We have 2 negative charges. So when 2 negative charges interact with one another, you're going to have repulsion. And the same thing happens here. When 2 positive charges interact, we also have repulsion. However, if we have a negative and a positive charge interacting, we're going to have something called attraction, which happens in our example of lightning. You're going to have a negative and positive charge interacting with one another, and the force is so great that clouds, which are usually good insulators, cannot contain it. So that's how we see our light.
Some examples of electric charge in nature would be thunder and lightning. Like she explained before, when 2 oppositely charged clouds collide, they form thunder and lightning, as seen in my drawing here. Another example would be electric eels. Electric eels naturally produce electricity. They use it for prey and for predators. And they produce enough electricity to stun a large horse or, sadly, sometimes kill themselves. Another example would be stargazers. Stargazers are similar to electric eels, but at a mild version, and they only attack small fish with their electricity.
Where does it shock you, on the top?
Oh shit! Spiders, well, baby spiders can use the electric charge waves in the air and use them to fly to a new location. Electric field. So the electric field surrounds an electric charge and exerts force on other charges in the field, attracting or repelling them. An example in nature of electric field would be bumblebees and flowers and their relationship with one another. So, since flowers are electric billboards, flowers have a negative charge and bees have a positive charge. The bees can sense the electric field around the flower and distinguish the fields between different flowers. So they can sense the shape of the flower, the color, and the size of the flower just by flying around it. As seen here, as Bill the bumblebee is flying around the flower, and he's sensing the electric field.
The electric field lines help show the direction of the electric field vector at that point. The closeness of the lines show the intensity of electric fields at that point also. So here we're going to have a positive and a negative charge. And you see that in the positive charge, it's what's giving off the electric field lines. And it's always going to be attracted to it's always going to go to the negative charge. So for conductors and insulators, we have conductors which consist of more free electrons or freely moving electrons, which are going to allow our electric current to pass easily through them. When you have an insulator, there is few to zero free moving electrons, so the electrostatic current is going to be pulted. So an example of a conductor can be metal, which is why a metal pole is more likely to be struck by lightning. And a good example of an insulator would be rubber. So for charging by induction, we're going to have a neutrally charged sphere, and we have a positively charged rod. Whenever you put the sphere and the rod close to each other, not touching but very close to each other, the positive ions in the sphere are going to be pushed out, and the electrons, the negative electrons in the sphere are going to be attracted towards our positively charged rod. And at the end, it's going to result in a negative charged sphere, and this is going to coincide with electrical.
So electrostatic shielding is a practice of reducing the electromagnetic fields in a space by blocking the field with barriers made of a conductive material. So we have a metal neutral sphere here, and when you introduce electrostatic shielding, when an electric field is introduced, the charges will move outward and the middle of the sphere will be neutral.
Ooh, that's gonna be loud.
An important application of electrostatic shielding is used every day for cars, planes, and other vehicles. And that's it's used for when, say, lightning strikes happen, and you gotta wonder, why exactly does nobody on the inside of the car actually, get hurt? And that's due to the electrostatic shielding that was mentioned before. The charge is drawn out, it stays towards the surface of the vehicle, while the inside stays neutral, and all the passengers remain safe. Now, it is because these charges are being drawn out towards the surface that we can actually get the electric flux throughout said vehicle. And this electric flux is given through electric flux, which is equal to electric field times area times cosine theta. And then there's Gauss's law, which also gives electric flux. However, it's for the charge that is inside an enclosed surface. And Gauss's law is electric flux, which is equal to charge over the permittivity of free space constant, which is 8.85 times 10 to the negative 12 coulombs squared over newtons times meters squared. And Gauss's law, it mostly refers to highly symmetric systems. Symmetry is an important concept in this, and it gets complicated if it's in a very deformed or distorted object, so to speak. This was Electric Currents Through Nature, and my name is Marco Garza.
Mariah Valdivia.
Deborah Mendoza.
And we wish you a happy day.
Thanks for watching.